you for coming to my presentation. My name is Shunsuke Akasaka from ROHM, Japan. The title of my talk is Temperature Dependence of Accuracy of Thermal Conductivity Hydrogen Sensor. The outline is as follows. Introduction and the properties of high temperature micro-hot plate and measurement results such as temperature dependence of sensitivity to hydrogen and CO2 and improvement of the accuracy of hydrogen sensing. Finally, I'll conclude my presentation. This slide shows the principle of thermal conductivity hydrogen sensor. Thermal conductivity gas sensing method is gas sensing method using heat dissipation rate from a heated membrane. This illustration shows the cross-section of micro-hot plate. When the membrane is electrically heated, heat dissipates into the ambient gas. The heat dissipation rate depends on the thermal conductivity of the ambient gas. This table shows the effect of the thermal conductivity. The thermal conductivity of pure N2 nitrogen is lower than that of hydrogen, so if the hydrogen is mixed in the nitrogen, the thermal conductivity increases. The heat dissipation rate is greater in hydrogen mixed nitrogen than in pure N2, so the membrane temperature is lower in hydrogen gases. So the concentration of hydrogen can be deduced from the temperature of the membrane. This table compares three types of hydrogen sensors: thermal conductivity, catalytic combustion, and semiconductor. Catalytic combustion and semiconductor use catalyst. So when the catalyst is poisoned, sensitivity drifts. Conversely, thermal conductivity sensor doesn't use any catalyst, so thermal conductivity sensor feature long-term stability. On the other hand, the impact of influence of interference gases is large because it only measures the thermal conductivity of the ambient gas. The lower detection limit is as high as 1%. So conventional thermal conductivity gas sensor cannot be used for 0.1% hydrogen leak detection. So our objective is to improve the accuracy. This graph shows the temperature dependence of thermal conductivity of the several gases. N2 and air are base gas, and they have similar thermal conductivity. And the target gas is hydrogen, which has much higher thermal conductivity compared to the base gas. The interference gas are CO2 and H2O, or water vapor, which has lower thermal conductivity compared to base gas. H2O is the main interference gas for the detection of hydrogen in air. Interference gas effect is as follows. When interference gas mixes in, the thermal conductivity decreases, leading to an underestimation of the hydrogen concentration. The influence of the interference gas can decrease at high temperatures, owing to the small difference in the thermal conductivity between air and H2O. So if we can prepare a high temperature micro-hot plate, we'll be able to achieve the high accuracy thermal conductivity hydrogen sensor. This is the process flow. This slide shows the process flow of high temperature micro-hot plate. SiON is deposited by plasma enhanced CVD, followed by sputtering, reduced TiO2, and platinum on silicon substrate. Platinum is patterned by photolithography and dry etching. After reduced TiO2 sputtering, reduced TiO2 is patterned by dry etching, repeating from A to C. Silicon substrate is removed by deep RIE. The platinum is covered, encapsulated with reduced TiO2 with or barrier layer. This is an optical image of micro hot plate. In this area, silicon substrate is removed and only membrane exists. This slide shows the heating property of the micro hot plate. As the heater voltage increases, the platinum resistance increases. The membrane temperature was reduced from according to this formula. And this graph shows the relationship between heating power and membrane temperature. This micro hot plate can reach 700 degrees C, which is well above the 400 degrees C, which is our target. This slide shows the evaluation system of thermal conductivity gas sensor. The micro hot plate was set in the inert gas chamber, and hydrogen and CO2 concentration was controlled by mixing nitrogen, hydrogen, and CO2 gases. Instead of A2O, CO2 was chosen as an interference gas because CO2 has a similar thermal conductivity to A2O, and CO2 concentration is easy to control. The heater was electrically heated, and the heater temperature was set below 350 degrees C to avoid an unexpected explosion. This slide shows the temperature dependence of sensitivity to hydrogen mixed in nitrogen. This graph shows the hydrogen concentration dependence of the ratio of resistance change of platinum temperature sensor. As the hydrogen concentration increases, the thermal conductivity increases, and so the membrane temperature decreases, resulting in decrease of platinum resistance. The color indicates the temperature in base gas N2, nitrogen. The absolute value of the slope of each line represents the sensitivity. This graph shows the temperature dependence of sensitivity to hydrogen concentration. Sensitivity to hydrogen slightly decreases at higher temperatures. This slide shows the temperature dependence of sensitivity to CO2 mixed in nitrogen. As the CO2 concentration increases, the thermal conductivity of the mixed gas decreases, resulting in membrane temperature increase. So the platinum resistance increases. This graph shows the temperature dependence of sensitivity to CO2 concentration. We can confirm that sensitivity to CO2 drastically decreases at higher temperatures. So the sensitivity to CO2 drastically decreases, while the sensitivity to hydrogen slightly decreases. The sensing accuracy was reduced by dividing sensitivity to hydrogen by sensitivity to CO2. This graph shows the temperature dependence of sensing accuracy, and the sensing accuracy increases at high temperatures. And the hydrogen sensing accuracy increases 2.5-fold at 340 degrees C compared to operating at 90 degrees C. So the And the sensing accuracy can become much higher by heating above 400 degrees C because the difference between the thermal conductivity of base gas and CO2 decreases. In conclusion, we investigated the temperature dependence of sensitivity to hydrogen and CO2. High temperature micro hot plate can be heated above 700 degrees C. Sensitivity to CO2 drastically decreased, while sensitivity to hydrogen slightly decreased at high temperatures. The influence of CO2 as an interfering gas can be reduced at high temperatures in a nitrogen-based gas. Hydrogen sensing accuracy increased 2.5-fold at 340 degrees C, owing to a significant decrease in sensitivity to CO2. Thank you for your attention.